x equal to 0. So this is all on an open set. Bix equal to 0 for all x in E. In particular, we have a trivial looking consequence. Dxi is not 0. Now, these statements, both the main statement and this in particular thing, as usual, they should be understood only in terms of, their action. After all, the only meaning a differential form has is how it acts on a K surface. So from that point of view, this statement should be understood that dxi is not 0. So so what it means to say it's not 0 is that there is at least one K surface on which the action of dxi will give me a non-zero real number. Okay, dxi is not 0 if, of course, assuming if it is basic. Basic just meaning that all the in the multi-index I, all the indices are distinct and they're put in an increasing order. The distinct is the main thing. Okay, so if it's not in an increasing order, you can always make it. We have seen that we can always make it into an increasing order and then acquire a sign. So if the indices are distinct, then dxi is not 0. So this part. So how does one prove this? Well, basically, if omega is 0, you should, again, the proof essentially boils down to finding out for each multi-index I, even for the main proposition, for each multi-index I have to find a K surface such that dxi acting on that K surface is not 0. But for dxj acting on that particular K surface should be 0 for any other j not equal to I. Then I'll be able to isolate these functions bi and get what I want. So I'll prove this towards the end of the class rather than, I should have done this much earlier. I thought I had, but apparently I just realized I had not. So this is a very basic fact that these dxi's are not 0. So at least you have something. I mean, ultimately, the definition of differential forms should not end up saying that all differential forms are 0. So these basic forms are not 0. Now, in fact, right. What is the, yeah. The other thing is that, now let's continue with exterior differentiation. Yeah. So these two things, multiplication and differentiation, are the two most important things about differential forms. Simply because they are something which one has not encountered before. I mean, you can add differential forms, multiply them by scalars, and so on. We have been adding and multiplying by scalars repeatedly in various settings. But this form of multiplication and this exterior differentiation is something genuinely new, especially the differentiation part. And the main novelty of this is what I said last time, that it will turn out that decompose with D.
Sorry,
Yeah.
I pressed recording stop.
Oh,
Sorry.
thanks. Oh, yeah, very good. Yeah. Okay. Okay, good. Somebody has pressed it. Yeah, okay, fine. So, yeah, as I was saying, the main novelty of this exterior differentiation, which is kind of hard to explain, but we'll prove it today, is that when you do this twice, that operation decompose with D, you'll get the zero operator. So decompose with D acting on any form will give me zero. So, but before that, let's do an example. So let's recall quickly how we had defined it. So if f is a C1 function on E, so this is a zero form. F is in C1 of E, which is, we have identified zero forms and functions are the same. In this case, C1 functions. So df we defined to be sigma df partial derivative of at x and then dxi. And right, well, that's it. So so let's and then for a general form, which in this case I called it di bix dxi. We define d omega to be dbi wedge dxi. So these bi's are of course functions. Bi will be C1 functions on E. So I use the definition this function d of a function, and I put it here. So that's how I get this. And well, that's a definition. So this definition, as I tried to explain last time, is done keeping in mind various properties that we want. In particular, we would want d squared d of d to be 0, and d should satisfy some kind of Leibniz rule. D of a product should behave like our usual product rule for derivatives. Keeping all that in mind, this definition is made, and things will work out once if we do it like this. But before that, let me do an example from Rudin of a one form. Let's see. So f is in C1 of E, and gamma. So one form, no, f is a zero form, but I'm going to look at df. Df will be a one form, so it will act on a one surface. A one surface is a map from C1 map from gamma 01 to E. And so what is df? Well, we already defined what df is. Df is this thing here, but let's see how it acts on gamma. So for this, I have to use the definition here. Since these are all, I mean, this is a function of gamma is a function of one, rather f is a function of df is a one form. I don't have in the definition of the different of how a differential form acts. I don't need to worry about this Jacobian in this case. So all I'll get is summation over I dif at gamma t And then no, I mean, I do need to, what I mean to say is the determinant in the Jacobian will, the matrix will be just 1 by 1. So determinant will just give me gamma I prime t, tt. And this is something familiar. Well, what is it? I'm looking at the partial derivative. Remember, this was just df by dxi at gamma t, gamma I prime t. So this and summation over I. Can someone recognize what this thing is? Here, gamma is from, so I have mapped from 0, 1 to E, that is gamma, and F is from E to R. Now, what is this summation? What is the sum inside the brackets? Is there a short way of expressing that?
The derivative of the composition.
It is just by chain rule, it is just the derivative of the composition of, you compose F with gamma. F composed with gamma prime t dt. And by our fundamental theorem of calculus, this is just f of gamma 1 minus f of gamma 0. That's it. So the way one form, one form of this specific type, df gamma, way df gamma acts on the way df acts on gamma is just by this formula here. Okay. And this will be useful later on when we talk about closed forms and exact forms and so on. But for now, let's leave this aside. This is just a simple example, that's all. Actually, I should mention one thing. So this example is useful for the following reason. See, we know that if we start with zero forms, yeah, if I start with zero forms, then this D operator gives me a one form. So the question arises in various contexts, actually, whether every one form can be written as D of some function. Can any one form, in other words, is this D map from here to here, is it surjective onto? Can any one form omega be written as omega equal to df for some f in omega 0 question mark? And the answer is, well, definitely no. I mean, whatever E is, with an additional condition, it will turn out to depend very much on E. In fact, it depends on what is called the topology of E. But in this generality, whatever E, not put any conditions on omega, whatever E is, this will, you can always find some omega which will not. So an example is, no, if omega equal to x dy, this is something we had seen earlier. Then well, this calculation we had done earlier, and gamma is a closed curve. Actually, let me take this, we had done it for the specific case of the circle. I think I'd taken the interval to be 0 to 2 pi. So, but here now I have taken it to be 0 to 1. So I put a 2 pi here in this front of t. We had this calculation showed us that this actually gave us the area enclosed by this. I think there might be a sign, but up to sign, this was the thing. No, just pi. So just check this. I mean, it's an easy thing to check. So you can just use the definition and check. Well, what does this have to do with omega equal to df? But if omega equal to df on R2, so here E is R2. Then integral omega over gamma is f of gamma 1 minus f of gamma 0, as we have seen just now, which would be 0 because this gamma is a closed curve. That's the main point here. That gamma starts at this point and comes back here. So if it were d of something, the integral of omega over gamma would be 0, while here explicit calculation shows that it's not 0. I think it is pi. All right. So now let me continue with D, properties of this important operation D. So the first thing is, let's make some small simple observations. The first thing is, if Fg belong to C1e, if this, then D of Fg, the product of the two functions, would be, I claim that this is G times df plus f times dt. In other words, the Leibniz rule holds, at least for zero forms. The second thing is, if I take this basic form dxi, then do d to that, I get 0. So the proof is quite trivial. Well, as for 1, d of fg is by definition summation di fg and then dxi summation over a. Now these partial derivatives di fg is just the ith partial derivative. This of course satisfies the Leibniz rule. After all, the partial derivative is just the usual one variable derivative. When you fix all, basically you fix all the other variables and let one variable vary. So you do what does have the Leibniz rule here. So this is well, I f dig plus g dif and then dxi. So you just split the sum into two parts. The first one will give me f dg and the second one will give me g df. Now this is even easier. I just have to go to the definition. After all, how do I see this? dxi is just in this, I mean, I'm assuming I is dxi is a basic form. So its standard representation is just dxi equal to 1 multiplied by dxi plus 0 multiplied by all other dxj, j not equal to I. So in other words, in its standard representation, all the coefficient functions are either 0 or 1, and in fact there's only one. That's for the index capital I. So therefore, by definition, d of this would be, I would have to take partial d of this times this. So d of the constant function 1 times dxi plus d of the constant function 0 times gxj. Obviously, d of a constant function is 0. By definition, I mean, you basically d of any function, remember, was just this was the formula. So if f is constant, all the partial derivatives are 0, so you don't get it. So that proves this simple statement. Now comes the main thing. So let's call it a theorem. Let omega belong to omega, capital Omega k. In other words, it's a k form, and lambda is an m form. When I do this, d of omega wedge lambda. So as I've been saying, I want some kind of Leibniz rule for forms. Now the multiplication here is the exterior multiplication. So, well, the first term is okay. The second term would be, if it had been the usual Leibniz rule, it would be omega wedge d lambda. But it's not quite that. I'll get a -1 raised to k omega wedge d lambda. So this is the Leibniz rule in this new setting, the product rule for derivatives in the realm of differential forms and exterior derivative and exterior multiplication. d of omega is equal to 0. So actually, yeah, okay, fine. So this is it. So strictly speaking, if one should keep track of these D's with an index, for example, this omega ke will take me to D here, will take me here, and one more D, the second D will take me here. Yeah, that's another thing, by the way. Yeah, that's already, I mean, that's implicit in the definition. Notice that the way D is defined, D omega will be D bi wedge dxi, right? And dbi is a one form. So one form multiplied by a k form will be a k plus one form. So the D operation raises what is called the degree of the form by 1. So I have it like this. So strictly speaking, one should keep track of these maps by keeping putting an index dk here, dk plus 1, etc. So then it would be saying dk plus 1 composed with dk is the zero map. And this kind of formalism, this kind of properly labeling the D's is important when one looks at it, I mean, in detail. But for now, the point is that the D operation applied twice is 0. Let's just remember that. And the other thing to remember is D raises degree of the form by 1. So let's prove this. The first observation is that we can assume that, I mean, I don't have to deal with the full generality of all forms. Omega is Fi dxi. Lambda is, there's no, I mean, there's only a single index, so I don't need this. Lambda is G times dxt. Where F and G are C1 functions. Now, why can we assume this? Well, for the simple reason, because since, I mean, you start with the general one. See, this is what we are aiming for. We want to prove this. You start with the general one. Omega is summation of Fi dxi and so on. Then you expand this product. After all, this was the way it was defined. You can, you expand this product. Here there's a sum, here there's a sum, and you'll be left with a sum of basic forms. And then I have to take D of that. Likewise here. So I leave it to you to check this actually. So it's a small calculation. So check this. So what you have to check is that if you prove the proposition for these basic forms, we have proved it in general. Use the fact that or rather, since we have not stated it explicitly, first check that D is linear in the following sense. D of omega 1 plus omega 2 is D omega 1 plus D omega 2. And then D of, actually the constant thing you don't need. D of C omega equal to C times D omega if C belongs to R. So all these are vector spaces. This omega k is E and this dk's are linear maps. But yeah, so that's use that and then use the definition of exterior multiplication. Remember, the way we defined exterior multiplication was we define if omega equal to fi dxi, lambda equal to gj dxj, we defined omega wedge lambda to be fi gj dxi wedge dxj. This was the definition of omega wedge lambda. So when I do d of the left hand side here, linearity by linearity, I'll be doing summation d of each of these. Okay. So I'll be essentially ending up with basic forms. And the right hand side also, you have to look at see what you get. So anyway, I leave it to you to check that. The simple fact that you can reduce to this simple case. So once we have these basic forms, omega wedge lambda will be then f times g dxi wedge dxj. Now I want to take d of this. So it will be now the way we have defined things. Yeah, the only problem with this working with these tablets is it's kind of very cumbersome to go back several pages. So I have to let me just write down whatever I want to refer to. So remember that if I have this, I have this thing here. I defined it like this. But when I made the definition here earlier on, I assumed that everything was in standard form. Now, is it really necessary that everything be in standard form? In other words, of course, for the definition, you have to, it's okay. I made the definition, but once I make the definition, we can observe that even if this is not in standard form, still this I'll get the same answer if I do this. Note that even if RHS is not standard, we still have d omega is, I can use the same formula in other words. And how does one see this? Well, you have to go back to suppose it's not standard. What you start with is not standard. In order to use the definition of D, I have to put it in standard form. There's no option. But when I put it in standard form, what will happen? It's just that I'll acquire a sign here, right? So I'll acquire some -1 to the power something. Then I can do D of that. Then I'll get an expression like this, what I have here, but it's it's a slightly different index. And the -1 power will be sticking here. But then again, I combine this -1 power with this thing here and put it back in the original form. So I'll still get the same equation. So this is something which helps one in calculations. So you don't have to worry every time about putting it in standard form. When you see something like this, you just go ahead and apply, take D like this, okay? And we are going to use something similar here. So what I said about changing sign and all, you will see, I'm going to do it here in this simple case. So first, let me put it in standard form. Fg minus 1 to the power alpha and then in the standard form this would be dx that bracket notation. This is now a basic form. The term inside the brackets is basic. This whole thing is basic. So I can use the definition and write it as minus dfg wedge this. Now, whatever I said here when I was discussing this general thing, I said that use the minus sign to go back to the original form. I'll do it here. So I'll write it as minus 1 to the alpha and then dxi wedge dxj. So it's actually a very kind of, it seems like pointless, but because we put this minus 1 to the power alpha and the bracket, and then we didn't really use it. We again went back and removed that minus 1 to the power alpha and the bracket and put it in the original form. So why did we even do this? As I said, the only reason we changed this to this along with this sign is so that we can use the definition. The definition of D involved putting everything in the standard form. But as this calculation shows, even though this is not a basic form, I'm doing the same thing. I'm just taking D of this and wedging with whatever is there. See, that's which I would have done had this been basic. So what this calculation is, this small calculation is justifying what I was trying to say here, that even when you have an expansion like this, which is not standard, you can go ahead and take D. Well, it's slightly different here because I have dxi wedge dxj here. In this case, I don't have two multi-indices, just one I, but still the same logic holds. Yeah, maybe I'll give it as a homework exercise actually. I'll state it clearly and give it as a homework exercise, a homework problem. Yeah, so we were at this point. Now notice this bracket. This bracket I have over. So first I'm supposed to do this wedge and then this. Or rather first this and then wedge with this. But now I'll use the lemma. DFG we have already seen for zero forms. It was FDG plus G plus GDF and then wedge dxi wedge dxj. I will now split it into two parts, f dg wedge dxi wedge dxj. I'm doing everything very carefully because see, in this, it's a new kind of algebra that we are dealing with. Multiplication, even to prove multiplication was associative, we had to do a tiny bit of work. So we cannot take anything for granted when dealing with this. So let's go carefully. And then I get this. And then the second term is GDF wedge dxi wedge dxj. Now, the point is that, well, what is the stuff? Right. Right. So, the first one will give me f dg. Yeah, now I'll use associativity of multiplication. So I'll remove the brackets around this and write it as dg wedge. Oops, maybe not that. What I want is, yeah, I'll just first I'll interchange this and this. Do I want to do that? Dg wedge dxi. Yeah. So where was I? Yeah. So this one I'll write it as dg wedge dxi wedge dxj plus g times df wedge dxi wedge dxj. So I've used associativity. Now I want to interchange these two. So I'll write it as, so dg wedge dxi is equal to, so this was your homework problem, that when you omega wedge eta is minus 1 to the power omega wedge lambda is k times m lambda wedge omega. Here, this is a 1 form and this is a k form. So the product of the two degrees will be just k again. So I'll get minus 1 raised to k dxi wedge dg. So if I do that, then I'll get dxi wedge dg wedge dxj. And then here I don't have to worry too much. This is just df wedge dxi is just d. Right. So then this g I'll combine with dx. So this is just d omega wedge lambda. This is d omega. And g times dxj is lambda. So here I don't have to do much. I just write it like this. The first term, I'm still not done with it. Yeah. Right. So the first term f times
minus term.
Yeah, that I'm going to put now. Right now, I didn't need that. Oh, yeah, I already done that. So I should put -1 to the power k. I've already done that here. And then again, I do one more associativity. Instead of clubbing these two together, I'll club this and keep this by itself. So f times dxi wedge. This was, what was it here? dg right dxt plus the second term remains the same. This was d omega wedge lambda. Now we are done because this is f dxi is by definition omega, and this by definition is d lambda. So we have used associativity twice along the way, and then we also use the anti-commutative. This was the crucial part, that anti-commutativity of this exterior multiplication had to be used as well. That's how we pick up the -1 to the power k in the Leibniz rule here. So that proves this. Now the second one is more interesting because it's not clear. There is no analog of this in something that you would have seen earlier. After all, I mean, the Leibniz rule is just the same old Leibniz rule for functions, but with some slightly different, it's a variant of that. But this decompose with d being 0 is something, it's a new thing. Why is this true? In fact, the answer lies in just looking at starting with the simplest case, namely zero forms. Let's start with a C1 function. Let's look at d. By the way, we'll write it as d squared f. d of f. So we would expect this to be 0. Why is that? So let's see. So this is summation over I dif dxi. Now d, as I said, is linear. So d of the sum will be sum of various d's. dif dxi. Now let's use the Leibniz rule we have just proved. This is a 0 form, a function, and this is a 1 form. So that k which occurs here, since I've written this first, the k will be 0. So it will be d of dif wedge dxi plus there's no that -1 to the power k, which will be just 1 again, dif, then d of dxi. So this is 0, as I remarked in that small lemma, the d of xi, even if it's a multi-index also it's 0, but here it's certainly 0. So I'm just left with just this. And what is this? Well, f was a function from E to R, DIF is also certainly a function from E to R, the partial derivative function. So again, I'll have to use the same thing. Now I'll have to use a different index, dj. So dj DIF dxj wedge dxi. This thing is still there. So this was d of that. But remember that there was a summation, there was this sum over I. So let's throw that in as well. So d of f is summation over I, summation over j, dj dif dxj dxi, which is this. This we claim is 0. And why is that? Well, just look at the how things pair up. The crucial point are the following: dj dif equal to equality of the mixed partial. Ultimately, this is the heart of the matter. The mixed partial derivatives are equal. So I equal to 1 to n, j equal to 1 to n. On the other hand, see, this dj di, according to this, will occur with dxj wedge dxi. It will be the coefficient function for this particular thing. This will be the coefficient function for dxi wedge dxj. But we know that dxi wedge dxj is the same thing as minus dxj wedge dxi. So this term, j first and I second, will occur again in this overall sum with a minus sign. Dij, this is the same, but this differential form part changes sign. So pairwise, things cancel out. And you're left with 0. That's it. So this is so the two crucial takeaways from this are equality of mixed partial derivatives. The other thing is anti-commutativity of multiplication. Dxi which dxi is dx. So this plays without this both of these, you will not have this equation. You will not have d squared is equal to 0. So somehow d squared equal to 0 is capturing this condition that dji d equal to this. So in that sense, it's kind of, one should not think of d in a very simple-minded way as just taking derivatives. It is something slightly more than that, because there is this science involved. On the other hand, from a simple-minded point of view, it is like taking derivative, but it's sometimes it helps to think like that as well. But keep in mind that d squared equal to 0 does not occur in our traditional derivative setting. Now, yeah, I haven't really completed the proof. The proof was that I just proved it for a function, but it's quite easy to prove it for everything else as well. Now I take a general bi dxi, as usual standard. I want to do d squared again. Well, I just after I do D once, I get by definition this. Now derivative is D is linear, so I'll end up getting this. Again, I use this Leibniz rule. I'll get, so D of D squared of Bi wedge dxi plus minus 1. Now this is a zero form again, there is nothing here, plus D Bi wedge D squared D of dxi, which again we have seen that this is 0. Now the main point is that this is also 0 because of what we just proved for functions. So this overall is it's 0. So we just use the Leibniz rule. That's a new ingredient for the general form case, and you get it. But the heart of the matter is in what happens to just functions. That d squared equal to 0 for functions, it will capture everything. Okay, so now the proof is one thing, but it is you must understand that this very definition of D is not at all obvious why one defines it the way it is defined. And why does one want D squared to be 0? So it has a long history. So it'll, but as you'll hopefully, as we keep studying more about this, it'll become somewhat more familiar, if not completely clear. But at least you'll gain a working knowledge of it. See, it's one thing to be able to deal with it in the sense of do calculations and so on, and another thing to have a clear understanding. The second part will take more time for this D. Now, I'll just take 5 minutes and finish this stuff that I had stated earlier. That if omega is so something more elementary, this is all these functions are 0. As I said, the proof essentially involves so let's say suppose Bj V is greater than 0. I mean for some J and some V in E. The claim is that all these functions are 0. So suppose one of them is not 0, so that means it will not be 0 at some point. I'll assume that it's positive. If it's negative also, the proof will work with slight changes. So let that particular index be J1, Jk, where as usual, I mean, I've already assumed that it's in the standard form, so I have this. Now, this was before, I mean, this proposition was just after we introduced differential form. So I don't need to assume that these are C1. So just continuity is good enough, since Bj is continuous. If it is positive at some point, the point V, it will be so in a small ball around that. There exists h greater than 0 such that Bj x is greater than 0 for all x with norm x minus v less than h. Of course, you choose h so small that this ball is contained in E. Otherwise, B won't even be defined. So small ball, radius h, radius less than h. Let d equal to minus. So remember the goal is. I've not used the hypothesis yet. The hypothesis is that omega is equal to 0. So I'm going to construct a special K surface using this particular Bj, which will not be 0, which will contradict omega is equal to 0. So let's take minus 1. So this K cell in Rk. And my K surface is going to be phi of u is equal to V plus UR EJR, and this index R equal to 1 to K. So what I'm doing is, in geometrically, I'm just this this is V, and I'm adding a specific vector. So for every U in U which belongs to this K cell, so I have a K. So for every U here, I'm sort of adding to V some basically some part of U. Remember, I'm going only up to K, not all. This is in Rn. This is in Rn. This is in Rk. So what I'm adding is, this is essentially V plus this vector, UR1, URK, and then zeros everywhere. Oh, I cannot write it in this notation because where the UR occurs depends on EJR, not in E1, E2. So it's a bit messy to write in this coordinate notation. So let's just leave it like this. So, but anyway, you think of it as just adding to V, take U, and then out of that you concoct a vector and add to V. So this is anyway, this is a C1 function from this K cell to. So this is from D to Rn, D to E. Oh, why does it belong to E? This is certainly in Rn. It belongs to E simply because its distance, note the phi of u minus V, it will actually lie inside the small ball that we. So if I subtract V is just less than or equal to norm U which is less than H. Actually, I have to make a small change, I think. Because see this this is less than or so this is equal to norm of UR EJR, and then less than or equal to summation modulus UR R equal to 1 to K. K. But this U1, U2 will lie in these intervals. So the sum will be less than K times mod H, not mod H itself. So I might have to change that slightly. So maybe here to put KH here and this. But that's not the main point. The main point is, so since it belongs to the ball, therefore Bj of phi of u is greater than 0 for all u in D. I mean, that ball was chosen in so that Bj is positive in that ball and the image lies inside that ball. Yeah, the main point is that what does the differential form, the acting on the surface, look like? I want to claim it's not 0. Omega acting on phi. This is what we call denoted by this. Now, this one, well, if you go by definition, it will be summation Bi of phi, and then the Jacobian, what I call phi. Yeah, that's it. And this integral is over D. Well, right. Now, I claim that only one term will survive here, namely Bj composed with phi and then Jacobian of Pj. So why is that? That has to do with the way this thing is defined, this expression here. So let me just quickly write down what is phi I. Phi I would be the way I defined it. This was this phi I1, phi I phi I k. Now, as I remarked earlier, in fact, I was about to write in component notation, but then I changed my mind. If you look at this function, phi, and take an index at I, this will have all, in general, it will have, yeah, let me put it like this. So phi will be of the form phi of u will be of the form v1, every v2, I'm leaving some space deliberately, vn plus plus plus. Now, if I take an index set I and look at the components corresponding to this index set, if I is not equal to j, then what will happen? It's just that one of the, so this plus, yeah, first let me say the plus, either it will be 0 or it will be some UR is added to that. That's what I'm trying to say. When is UR added to that? Only those indices which correspond to EJR, rather JR. The ones indices coming from the multi-index J, there you will have UR added to that. Otherwise, it will be just zeros. So what will happen is that if you take this J phi I, if I is not equal to J, one of the component functions will be constant. It will be just V something. And therefore the Jacobian will be 0. So it's kind of messy to explain. So anyway, I told you whatever is there, but so I'll leave it to you to check. Check that J phi I equal to 0 if I not equal to J. That is the gist of it. And if I equal to J, it is 1. Well, so these two statements have to be checked. So this will be just Bj composed with phi on D, which is positive because of this. The image lands inside. So that proves it. So we assumed that for some multi-index Bj is not 0, and we concocted. The main thing was coming up with this function, the surface, K surface phi, which will make this omega acting on phi to be positive. And the way we came up with it, we ensured that all the other Jacobians are 0, 1 is. By the way, this is not the only way to do it. There are other ways of simple-minded ways of coming up with this phi, which will ensure that the same conclusion that one can get this. So you want to, the idea is always the same. You want to make sure that all the Jacobians vanish except one. So you can try to come up with your own, or if you want to prove this what I've written here, you will have to try some specific values, concrete examples, then you will see immediately. That's always the case with this combinatorial type of calculations. You just take specific values and the dimension to be low enough, then you'll get it. All right. Sorry, I went over time, but I wanted to finish this. So shall we stop here? By the way, there will be a quiz day after tomorrow. The material for the quiz will be the homework that I gave on Monday, that one. Okay, exterior multiplication.
Okay, sir. Noted.
Yeah. Noted? Yeah. All right. So we'll end it here today. Okay. Thanks.
Thank you, sir.